Munich. He's an expert on dynamical systems with a focus on multiscale analysis, stochastic bifurcation, and network dynamics. And today he will give a talk on GSPT for fast-slow PDEs. Please, Christian, the screen is yours.
So thanks to BS for the very nice introduction and invitation. So let me just quickly say a few words about the talk. What's the sort of today's plan? So the plan is that I will start a little bit slower because I think it's quite a sort of interdisciplinary audience, I would say. I mean, already the name of the chair where I'm giving this talk and dynamics control and numerics is pretty broad. So I thought I would spend really quite a bit of time motivating a little bit the problems so that everybody has the sort of at least background and understands why these fast, slow systems or these multi-scale systems are important and why we want to lift a certain theory from ordinary differential equations to partial differential equations, because somehow this is a sort of key topic in sort of, I think, almost all application areas that you could think of, you know, biology, physics, engineering, climate, whatever. The same problem appears over and over again, and we are trying to develop a little bit sort of a base theory in multi-scale PDEs for these different application situations. So let me say this is joint work with Maximilian Engel and Felix Hummel, and there's many other people who are currently joining. So there are future projects in preparation. And let me start a little bit with the background, introducing what these fast slow systems are and why they are important, and at least for ODEs that everybody has seen a little bit. Okay, so the classical textbook example, so second lecture of sort of undergraduate nonlinear dynamics, is the van der Pol oscillator. It's a relatively simple set of two ODEs, where in the second equation you have a small parameter, which sort of means that x formally is fast and y is slow. Yeah. So because the tiny epsilon says that y is effectively evolving slowly compared to x in most parts of phase space. Not everywhere, but in most parts. So how does this look? Well, you could sort of start with certain initial data in green and integrate them forward. And then you see indeed your intuition is correct. If you just sort of pick at random any initial data, first you mostly see movement in x because x is much faster than y. So Q here is a globally unstable equilibrium. You can check that this equation has a globally unstable equilibrium point at the origin. And indeed, these trajectories almost vertically fly away from this if you start near there. Horizontally fly away, of course. Yeah. So yeah, in this case, I've drawn it horizontally. Apologies. So now you could think, how do I analyze this behavior? So the natural thing as a mathematician would be to say, well, epsilon is small. Let us try to take the limit. So if you take the limit in this van der Pol oscillator, what you get is called the fast subsystem, because it's basically only the fast dynamics is evolving and y is basically acting as a parameter. So you have these horizontal sort of invariant subspaces, and within each subspace you have a dynamical system in X. And if you analyze that, you can quite easily check, okay, there are different regions. For example, in this sort of horizontal line here, you have three equilibria. You have one equilibrium in the middle that's unstable and two that are sort of stable, so you have bistability. And then if you go up in y in the parameter at the sort of top, you, for example, only have one equilibrium because you have changed y, and that equilibrium is actually globally stable and you get attracted to it. So you can analyze this fast motion in this called singular limit quite easily, because you somehow have reduced the dimension by taking this limit, because you can analyze each of these systems for y separately. Yeah? But somehow this doesn't give the full dynamics. Yeah? So the full dynamics is different. So in the full dynamics, you also at some point have to take into account the slow scale. So y will be moving at some point. And you do that by scaling time. So you go from the fast time scale t to the slow time scale s. So you slow time down by epsilon. This moves effectively the epsilon that was in front of the minus x in the second component, and it moves it up to the first equation. Oh, by the way, I think somebody is not muted. I hear some.
I'm sorry, yeah, as I'm not host because I left before, I can't unmute them. But if you give me the host back, I'm happy to take care of that.
Okay, let me quickly see if I can make you the host. So I think now you are the host.
Yeah, okay. I will.
Okay, just to, because that's always slightly, if it's beeping and blipping, then you can of course always unmute and ask questions. You are very much encouraged to do that. It's just that other sort of sounds can be tricky. Okay, so please ask questions, right? If you have something, unmute yourself and ask a question. I'm very much encouraged. So you scale the time, you go to a slow time scale. And if you do that, then you see that the epsilon moves from the right-hand side here near the x to the top here over to the dx ds. And then you can again take a limit, which is called the slow subsystem because it's on the slow time scale. And you indeed see that that's a non-equivalent system to the previous one because it's a differential algebraic equation. So you're basically on a manifold on this cubic curve, and on this cubic curve, there is dynamics. Minus x is easy to check, so you have downward dynamics on this cubic curve here, you have downward dynamics here, upward dynamics on the left side of x is equal to 0, and you see that there are two sort of singular points, these are called fold points, where you actually have that sort of the dynamics on the slow scale become singular, and on the fast scale, these are actually, if you are well-versed in bifurcation theory, you are seeing that these become saddle node bifurcations or fold bifurcation points in the fast subsystem. And thereby, this is the name why they've acquired the name fold point. Yeah. So now you need to combine the dynamics of the slow subsystem and the fast subsystem, which are both one-dimensional, to get the dynamics of the full system of this ODE. Well, how do you do that? Well, you sort of draw orbits geometrically, and you can check these sort of horizontal orbits. These come from the fast subsystem. So these are basically orbits that are sort of these horizontal guys that get attracted to this right branch. On the right branch, you draw an orbit that's in the slow subsystem that was pointing downwards. At the fold point, you can guess that, well, since the flow is directed here to the left and on top at the fold point to the right, you make these fast jumps. And then you again have a slow dynamic, fast dynamic, slow dynamic, fast dynamic, and so on. And you see that you've constructed in the singular limit epsilon equal to 0 by combining the fast and the slow subsystem a candidate for a periodic orbit. So you're expecting that indeed this van der Pol oscillator is oscillating and has a periodic orbit. And well, if you numerically integrate that, that's exactly what happens. That's one of the green initial conditions I had before. It first flies towards this sort of black guy, the sort of thick black curve, and then it tracks this very closely. There's a slight deviation in epsilon here near this knee, near this fold point. It makes a jump, then it again has a slow piece, it makes another jump, and indeed, this orbit gamma epsilon is a perturbation of this candidate orbit gamma 0. So you indeed have geometrically constructed a highly non-trivial orbit for a multiscale system, namely an orbit that has this sort of relaxation type behavior. That maybe you have seen somewhere in textbooks. So that's sort of a quick run through. Well, in an undergraduate course, it would take a little bit longer to run this through, but here I can be a bit quicker, how you can use these multiscale techniques to construct different orbits. Of course, if you want to prove these things, you need to make proofs for all of these pieces. You need to show that indeed there is a true periodic orbit. You need to prove every phase of this orbit that this is correct, that indeed this thin numerical line is a correct line. Yeah. All right, so let me do this in more generality. So you can do this for ODEs in much more generality. You can say I have sort of m fast variables and n slow variables, and I have an ODE that is a fast slow system in standard form, where just I have generalized this van der Pol example to a general vector field. Yeah? I can rescale time again, which moves the epsilon from the bottom right to the top left. And then I can take limits and I get the fast subsystem and the slow subsystem that are still a parametrized system for the fast subsystem, where y, the slow variable, is acting like a parameter, and the slow subsystem where you actually have a differential algebraic equation, where you have an evolution equation on, well, a manifold, or more generally on an algebraic variety, or more generally even on a set effectively. Yeah, that's defined by these 0 conditions. Yeah. Okay, so what are the base techniques? So the base techniques, we have already seen that somehow this critical manifold, this cubic curve that defines the equilibrium points for the fast subsystem and that defines the algebraic constraint for the slow subsystem, that was this cubic curve in van der Pol, that is very important. So we give this the name critical manifold, and we say that this is called normally hyperbolic if you linearize around it in the fast direction, and there are no eigenvalues of the resulting matrix with 0 real part. So this is basically a generalization of the concept of hyperbolicity of an equilibrium point to hyperbolicity along an entire manifold. Let's assume for now this guy is a manifold for, sake of argument. Later on, I will also come to some manifolds that cross, so two lines that cross, but you can think that C0 is a manifold for now. And well, you call that manifold attracting if all the eigenvalues have negative real part, you call it repelling if they all have positive, and you call it saddle type if there's some repelling and some attracting, if it's normally hyperbolic. So roughly speaking, if you go back to our van der Pol example, you basically see that this right branch here is attracting, because if you take this first equation, you differentiate in x and you linearize and you plug in a point on this gray curve, you see that indeed the single eigenvalue that you are getting is negative. And in the middle part, it's repelling, so you again linearize, etc., etc. Yeah? So this is standard applied math in some sense. All right. So what are the techniques in standard ordinary differential equations, fast flow system theory, or more generally from a geometric viewpoint, this has become known as geometric singular perturbation theory, because we are trying to bring in this viewpoint of geometry. There's usually many, many techniques. I will only highlight some of them, and there's always three layers of techniques. There are techniques that are more asymptotic, so basically asymptotic expansions. There are techniques that are sort of analytic / geometric, where you're sort of trying to get a grip on the sort of results without sort of plugging and chugging the expansions in full detail. So you're implicitly doing the expansions by geometric techniques. And there are, of course, algorithmic techniques where you try to compute these objects. And then these techniques are split up depending upon the regions of your multiscale system. So where are you in this example of the van der Pol oscillator? Are you near a normally hyperbolic piece? So near the sort of gray bit of this critical manifold where you have normal hyperbolicity? Then the sort of typical techniques would be regular asymptotic expansions from classical asymptotic analysis. In theorem that I will state on the next few slides, the Fenichel-Tikhonov theorem is a geometric theorem that tells you how a normally hyperbolic part of this dynamical system locally perturbs, and the algorithmic techniques that calculate you in high-dimensional systems these manifolds. So ILDM is invariant low-dimensional manifolds, CSP is computational singular perturbation, ZDP is zero derivative principle. So all of these algorithms have fancy names. So today in my talk, I will focus on the geometric viewpoint and a little bit on the analysis, because I cannot talk about all of this because it's just too much. Yeah? So I will try to focus on a few aspects that you see how this theory is in action. But there are also points where you have, for example, a transition towards a normally hyperbolic piece and then a slow piece afterwards, like in the van der Pol when you jumped, and then after the jump, you get caught by the manifold and you move on it. Yeah? So this is this piece. You have a fast jump and you get caught by the manifold, you move down. So there you need what classically would be done by asymptotic matching. The modern geometric viewpoint would be something like exchange lemmas, where you geometrically match certain manifolds. And for algorithms, it's usually useful if you have such transitions to transition from forward problems, so initial value problems, to boundary value problems, because this removes the stiffness actually. Yeah. So I'm not going to talk much about this second part of the transition from fast pieces to normally hyperbolic pieces on a slow manifold. The point I am going to talk about is these sort of fold points, or these special points where you have bifurcation points where normal hyperbolicity is lost, where you can, for example, transition from a slow piece to a fast piece. Yeah? There you also classically would try to do matching, just the matching is vastly more complicated. Yeah? Geometrically, what you would do is something called the geometric blow-up technique. It doesn't have to do with PDE blow-up in the sense of solutions becoming unbounded, but it's a geometric blow-up technique, a geometric desingularization technique. And algorithmically, you would try to detect these points by bifurcation detection algorithms, like numerical continuation, for example. So what I'm going to tell you is basically that we try to generalize these Fenichel-Tikhonov theorems and these blow-up techniques to PDEs. So first, I have to explain you how they sort of roughly work for ODEs. Okay, so that's the sort of goal of this. So, well, let me do a little advertisement. This has links to basically every area in applied math. You can't find one where this is not used, I would claim. There's always a problem where these sort of multi-scale structured systems, here it's only in time, but of course you could also do that in space, where these sort of multi-scale structures appear. It has links to basically all the sort of areas of differential equations. You can also do this with stochasticity if you like. Yeah, so there's a whole area of stochastic multiscale systems. And it has also links to all sorts of abstract sort of theoretical branches of mathematics. Yeah, to algebraic geometry, there are deep links. To combinatorics and polytope theory, there are links. To non-standard analysis, there are links. So this area is somehow quite well connected as a key working horse problem for many people who work on it, implicitly or explicitly. Yeah. And well, there's a little commercial break. So I studied 4 years in the US, so I have to do a commercial break. And so here's the commercial break. So I've written a little book about this. It's not that little, maybe with 800 pages, but this summarizes for ordinary differential equations all of the sort of base approaches to multiple timescale dynamical systems. So if you ever wanted a reference, I sort of would recommend that. Very good. So what is this Fenichel-Tikhonov theorem? Remember, this Fenichel-Tikhonov theorem was about taking a normally hyperbolic piece, so these gray pieces that are away from these two blue fold points and the van der Pol oscillator, and trying to perturb it. So what it says is you take a compact piece of this gray piece, so S0 is a compact normally hyperbolic submanifold, and then you assume that sort of epsilon is sufficiently small. Then for any sort of epsilon that is sufficiently small, there exists a locally invariant slow manifold that's diffeomorphic to this limiting object, to this S0. It has a small distance from the limiting object in Hausdorff distance, and the flow on it approximates, or is well approximated by, no matter how you want to put it, is well approximated by the limiting flow of the slow dynamics. And the similar conclusions hold for the stable and unstable manifolds, that mean all the manifolds that in the fast directions are going towards or away from this normally hyperbolic piece. So in van der Pol, it's pretty easy. So basically you apply this theorem on these sort of typical types of pieces. So let us pick such a box, or this box over here, this magenta type box. And in this magenta type box, you can easily check that the critical manifold is normally hyperbolic. You differentiate and you see that indeed there's only one eigenvalue in these boxes and it's always negative. So this is satisfied. And then you indeed get a piece of this sort of gray bit that is perturbed, and this gray bit will be attracting, and the flow on this gray bit will be similar to the slow flow on the critical manifold. So for the limiting system when epsilon is equal to 0. And indeed, it is, because if x is negative, the flow is pointing upwards, and here the slow flow is indeed pointing upwards. And you see that the numerical orbit, this thin line, very nicely tracks this so-called slow manifold as epsilon. Yeah, it tracks it very nicely, and at some point, then it, of course, at the fold point where you lose normal hyperbolicity, it jumps. So this Fenichel theorem roughly tells you that somehow you can geometrically convert a problem near a normally hyperbolic object to a regular perturbation problem where you have a regularly perturbing sort of nearby object that allows you to approximate the dynamics very nicely by the limit, or vice versa, the limit approximates the perturbed object. So they are close in distance and they are close in dynamics. All right, so this is used everywhere, really, because it's one of the few ways how we can dimension reduce in mathematics, and rigorously dimension reduce. There's not many ways. There's symmetry, there's maybe some integrability, and then there, for any general dissipative system, there's more or less only this. Yeah? You don't have much more. Yeah? All right, so what is this blow-up theorem, this blow-up method? This blow-up method is a method that works for points that are not normally hyperbolic. So roughly speaking, it tries to attack the points that are at the van der Pol here at the top and here at the bottom. Because there you cannot apply this Fenichel theorem, because if you differentiate, you indeed see that there's a 0 eigenvalue in the fast direction. Huh? So, but this theorem, well, there's a meta theorem that people found, that there's a geometric transformation. I don't go through the details. If you really want to read the details a bit, roughly speaking, there's a polar coordinate type transformation of such points that blows these points up to higher dimensional objects. So the idea is you take such a point, for example, the knee point and the van der Pol, you locally look at this point. So locally, this point is basically like the gray bit is more or less locally like a parabola, yeah, because it's a local minimum here. So let us transform this to something that locally looks like a parabola. Let's attach epsilon to the equations formally to get 3 ODEs. Yeah, I can do that. Epsilon is a parameter, epsilon prime equal to 0. I can do that. then in this three-dimensional phase space, epsilon equal to 0, x equal to 0, and y equal to 0 becomes an equilibrium point, right? So the singular limit, so when epsilon is equal to 0, becomes in this extended system an equilibrium point. And that equilibrium point as an equilibrium point of a three-dimensional ordinary differential equation is not hyperbolic, because if you linearize in this system, you see that all the eigenvalues are zeros. Right? You can do this in your brain, right? Differentiate in x, differentiate in y, differentiate in epsilon, do all the differentiation. Yeah, then the eigenvalues are at the origin all very easy. Yeah? At least there is 1, 0. Yeah, that's clearly there. Yeah, and here you see, while the matrix is not identically 0, but if you differentiate, then this becomes on a subdiagonal. So the matrix indeed on the diagonal has all zeros if you do this in your brain. But you can take this sort of blow-up transformation. What it does, it's a singular coordinate transformation that takes a point and blows this point up to a higher dimensional object, like in this case, a sphere. And on this sphere, you can actually find new dynamics that can help you. And in this sort of new dynamics on the sphere, the dynamics becomes partially hyperbolic in many cases, meaning what you have done, you don't have to understand the details here. What you have done is you have taken a very singular point, you have blown it up to a bigger geometric object, and in exchange for going to a more complicated space, you are allowed to use linear analysis techniques, right? Because if something is hyperbolic, it means that the matrix that you got from linearization indeed has eigenvalues that are away from the imaginary axis. So this means you have exchanged a more complicated geometry for the allowance to actually do linear analysis. I guess that's sort of something, hopefully a principle that's acceptable for any sort of applied mathematician, right? This sort of trade-off. Huh? And the sort of beauty of this is that in many cases this works, and in finite dimensions it's relatively easy to calculate. I mean, you can even play with it and try to do it with polar coordinates in the plane, and you will see that indeed it works. So polar coordinates are really fun. Yeah, so you can do this also in the plane for an equilibrium point in the plane that is singular. Try to change to polar coordinates, do a time rescaling, and then you see indeed the stuff that comes out is suddenly hyperbolic in many cases. Good. So there are these methods to treat these two regions. Let me back up a little bit. So there's this normal hyperbolic parts where Fenichel-Tikhonov applies. And there's this part where you lose normal hyperbolicity, where this geometric desingularization sort of is the important technique. Okay. Good. So this is the background. And now we want to go to PDEs. So how much time do I have roughly left? So is sort of 25 minutes to half an hour okay, or?
25 minutes would be perfect. Okay,
I will do 25 minutes then exactly. So we want to lift this now to PDEs. And maybe many of you are PDE analysts, and let me explain now some of the difficulties why lifting this to PDEs is actually really tricky. So first of all, let's start with a PDE that somehow is the closest in dynamical systems theory to ODEs in some sense. At least many results have been proven in the past where you can generalize sort of certain ODE type ideas to PDEs. And this is reaction diffusion equations, right? So let us start with reaction diffusion equations to get a little bit of a feel. We have proven this for much more general systems, by the way, but let us think for now, reaction diffusion equation, one-dimensional bounded domain with sufficiently nice, say, Neumann boundary conditions on a nice compact interval. Okay, so you can go much nicer, I guess, in terms of PDE regularity than this. So, and we take now a fast flow system where you have sort of a dynamic in V that is scaled by epsilon. So you have diffusion of this, say, chemical species, for example, and reaction, but the diffusion and the reaction are much slower sort of compared to the scale, at least formally in the equations, to the scale of the U guy. So all I've done, I've basically taken my previous fast flow system and I have sort of added diffusion terms. So to have a background a little bit, second advertisement break. So it's a bit like in the Super Bowl, you have plenty of advertisement breaks. So second advertisement break, if you want to learn more about these sort of PDE dynamics viewpoints on partial differential equations, you could have a look at my second book on PDE dynamics. So today's goals will be, we want to try to do Fenner theory for these fast slow PDEs, and we want to do geometric blow-up or geometric desingularization for these fast slow PDEs. Yeah? Good. So here's the overview of the references. Let me maybe go through them one by one. So the first paper that I've written with Felix is actually a paper where we try to generalize Fenner theory to infinite dimensional systems and in much more generality than just reaction diffusion. So we can do all sorts of semi-linear PDEs effectively. Yeah? And we give a general setting for these, and we try to A, find slow manifolds in infinite dimensions, and B, even if there is no slow manifold, we still find that there are certain approximating properties between epsilon equal to 0 and epsilon positive. Okay, this will appear soon in commentary. The second paper that we have written, which is sort of with Maxi Engel, there we generalized the blow-up method. So that's the sort of method how you can actually do this, and we did this for a specific type of fast-slow reaction diffusion equation. Yeah, I will talk about this second. So there the clue is to somehow pick a particular good problem, a good reaction diffusion equation, and try to sort of discretize. So there are many possible generalizations of the blow-up method, but here we are basically inspired by numerical analysis and we will discretize. I will show you how this is done in a second. And then there's the third paper where we are connecting the more abstract construction approach of slow manifold theory to the approach of discretization, and we are comparing a discretized to an abstract slow manifold, and this has recently appeared in proceedings of the AMS. Yeah? All right, so I will explain today a little bit in the last 20 minutes or so plus X what these three papers are about. Yeah. Okay, so what are the problems? Let me start with the problems in infinite dimensions. So let's start with a linear guy. And let's take a linear abstract evolution equation where you have an epsilon in the second sort of equation, and in the first equation, there's no epsilon. Of course, you can sort of write formally the solution semigroup in many cases, if A and B and L, L1 and L2 are sufficiently nicely defined. And you can also define what should be the critical manifold. It's just an infinite dimensional object that's given by, solving a PDE, for example. In this case, if A would be a, usual Laplacian and L1 would be, a matrix, or A would be a typical diffusion operator, and L1 would be a matrix, then this would be just something that lives in an infinite dimensional space. Yeah, you could think that all these domains and reaction diffusion equations, in the end, it boils down to classical Sobolev spaces. Yeah, so no sort of major sort of trickery here. Yeah, so what is the perturbed C epsilon of this object? Well, so the best available theory that is there is if you have a certain continuity as epsilon goes to 0 for the semigroup in a C1 norm. So this means you need some differentiability of this semigroup, and you also have a quite strong requirement that says the semigroup with epsilon equal to 0 is very close to the semigroup with epsilon positive. Unfortunately, this only works if the second component in V, that sort of the B, which we think of, for example, a differential operator in our case in a reaction diffusion equation, if B is a bounded operator. But that's not true, right? I mean, for a reaction diffusion equation, B is just the Laplacian, and the Laplacian is just not a bounded operator. So you are running into trouble because somehow the Laplacian gives you something that potentially can be very big and unbounded, and the epsilon gives you something that potentially in the limit is 0. So intrinsically speaking, the Bates theory is working, which is a brilliant theory, by the way. I mean, it's a very nice theory that was developed by Peter Bates and collaborators in the early 2000s and maybe the late 90s. So depending on when this was written up first, it's a brilliant theory, but it sort of cannot treat the case very well when there's sort of epsilon going to 0 and B becoming sort of unbounded. And then you are having this sort of typical problem in singular perturbation theory and applied math. One guy is going to 0, the other guy is going to infinity. Then what do you do? Okay, second problem. The splitting into fast and slow modes is by no means obvious. Before, we had this nice splitting that the first equation was always giving us the fast guys, and the second equation, the V, was giving us the slow guys. This actually also doesn't work anymore. The reason for this is that before we were on a finite dimensional phase space, and on a finite dimensional phase space, if I have eigenvalues, I can always find for a finite dimensional subpart of the eigenvalues a uniform bound. In infinite dimensions, I cannot give a uniform bound on the eigenvalues of an operator, for example, of the Laplacian. So let's take the two heat equations, let's expand them in Fourier, and let's look at the eigenpairs. And well, you see that some of the modes that in the V equation technically would be small, or slow, they actually become large if you go further and further down the chain of the eigenvalues. At some point, the eigenvalues might become very, very large. But if they become very, very large, for any fixed epsilon, the modes actually become very, very fast as well, which means some of the slow modes from the V component effectively become fast modes. So this means somehow this sort of standard splitting into fast and slow fails, and you need to think of a way around it. And the idea is you basically take a splitting of the eigenvalues and you somehow group all the eigenvalues that are higher than a certain mode, you make them all fast, and what remains is only a certain number of eigenvalues that effectively really give you slow modes. And you can only do that if you have a spectral gap. Of course, if the eigenvalues are not well separated, which unfortunately in some dimensions actually happens, the eigenvalues are not well separated in certain dimensions for certain problems, even with the Laplacian, then you can't do that. But we still can do approximation results, but some of the geometry only works with spectral gaps so far. Okay, third problem. What we want to prove is a Fenner-like theory that's well sort of localized in space and time. So remember the van der Pol oscillator, we had this nice little region and we had a little sort of piece of the manifold that we were perturbing for epsilon positive. So we nicely localized that in time. So we also want to localize these critical manifolds and slow manifolds for infinite dimensional PDEs locally in space-time. There is indeed a theory that's sort of similar, but it's extremely global. So there's this stuff on inertial manifolds, which can be viewed as finite dimensional, fully invariant, globally attracting manifolds. So they can be sort of viewed as global slow manifolds in some sense. So manifolds that are sort of globally attracting, very quickly, exponentially, you get there, and then you have some sort of effective slow dynamics on that manifold. But what we want to build is a completely local theory of pieces of manifold in infinite dimensions. So infinite dimensional Banach manifolds that are sufficiently localized. Right. Okay, we need to solve that issue. And then there's even more. Even more issues. There's an issue that, yes, it's well understood in some equations that there's fast and slow dynamics. It's well understood there is scale separation, and it's well understood that you can sometimes construct slow manifolds by hand in PDEs. For example, a classical case would be the Erlangen equation, where you know that there's effectively a slow manifold where you take an initial datum for the Erlangen equation with small diffusion. The initial datum evolves and it forms fronts. These fronts are very sort of sharp, and these fronts evolve at a very slow scale. So there's first fast dynamics where you land on a manifold. The manifold is parametrized by the coordinates of the fronts. And then these coordinates are slowly moving on the longer time scale. And eventually some of these fronts are colliding and then you fall off the manifold and so on. And you can actually construct sort of approximately invariant slow manifolds for specific problems if you somehow can guess the good coordinates. And here people would be able to guess the good slow coordinates because the good slow coordinates are just the coordinates of the positions of the interfaces, which are moving slowly on a long time scale. So, but we don't want that. We want this to be a general theory where you don't have to guess the coordinates, right? Maybe you don't know what the coordinate parametrization is. All right, so then let me check the time. Yes, very good. So now I can explain a little bit of the results. Okay, sorry for this long setup, but I think it's important because otherwise you don't understand where this problem is coming from. Now we are in the sort of abstract setup. So this is the setup we're actually working with in the paper. So suppose you take two Banach spaces. This would be your phase spaces in infinite dimensions. Take closed linear operators A and B that generate nice continuous semigroups with certain growth bounds. Of course, stuff like Laplacian satisfies this on nice Sobolev spaces, on bounded domains. You can take dispersive equations if you wanted to, if you modified this a little bit. You can take all sorts of other stuff that generates all the nice things that you want. Then you take sort of, well, effectively Sobolev spaces, but we do it more abstractly. We take interpolation, extrapolation scales, which is effectively a scale of Banach spaces, excuse me, that are stacked into each other. So roughly speaking, it's like having Sobolev spaces and they are stacked or embedded correctly into each other. Yeah. Good. So we assume that we really localize the problem. So the idea is we first cut the problem, we localize, and then we assume locally after the cutting, we actually have local Lipschitz conditions for F, G, and we actually also have some sort of true sort of nonlinearity. So meaning we put all the linear stuff in A and B, and we actually put all the nonlinear stuff in F and G locally. Yeah. So we localized effectively near a point or near a region. Then we assume that locally we are attracting. So let's just first do the attracting case, meaning the fast dynamics are attracting towards this critical manifold or a piece of the critical manifold. And then we also take an abstract V equation subsplitting. So this means the slow modes will be subsplit. This is an important point. So we do a subsplitting of some slow modes from the V equation that are indeed slow. Then there is a spectral gap. And then there are some modes that are actually fast. And the subsplitting is controlled by a second parameter, zeta. So roughly speaking, the zeta is chosen according to the spectral gap. And via that, what we will actually have, we will sort of separate this problem into a sort of finite dimensional slow bit and an infinite dimensional fast bit. But the infinite dimensional fast bit, well, will be actually the sort of modes that come from the last modes of the V's. Well, sometimes you can even do infinite, but I won't go into the details. Yeah, you should think finite, slow, infinite, fast for simplicity. Yeah, for your brain, it's easier to understand. So here's the theorem. So roughly what this says is, even in infinite dimensions under sufficiently hard conditions, you indeed get slow invariant differentiable manifolds. These are Banach manifolds in the spaces basically that live in X and Y. So you can parameterize, this is exactly what we have for the van der Pol, you can parameterize all the fast degrees of freedom over the slow degrees of freedom. The slow degrees of freedom are sort of all the slow degrees of freedom plus what we have cut off. So we have thrown away some fast guys. Yeah? And then you can actually show that this manifold and the limiting manifold is described also as a graph, that this limiting graph is actually close to the true graph modulo an error of all the additional fast modes that are small. So this is the spectral gap condition, this NS zeta minus NF zeta. So this you can only make small if you actually have a true spectral gap in the problem. If you do, then indeed what this says is you do get a slow manifold for infinite dimensional PDEs locally. Yeah? Okay. Somehow, if you are deep in this area, you would think, yeah, you know, I buy that. If you combine all the right techniques from the right areas and the right ideas and do the right cutting and everything, you sort of buy that this should be true. The method of proof is pretty classical in some sense. You use Lyapunov-Perron, which is an iterative technique to actually construct the manifold as a graph. So what you do is this function h epsilon zeta, you construct that by a typical iterative procedure, and then you use Banach's contraction mapping principle to, in the end, show with enough a priori estimates that indeed your iterative procedure converges to this graph. Yeah. Of course, yeah, this is 40 pages of technical calculations, but in some sense, the nice part here is if you do all the right splittings and utilize sort of the knowledge about what stuff is fast, what stuff is slow, and how to truncate and how to localize, you can generate, in some sense, a Fenechel type result in infinite dimensions. That's very useful, right? Because these equations here appear everywhere in science, engineering, physics, biology, whatever you want. Yeah? All right. So now there are some examples. I should claim, you know, we have applied this to a geoscience model. So this is a model for the North Atlantic meridional overturning circulation. So Gulf Stream, basically, where you can apply this. We have applied this in neuroscience or excitable systems or math biology to the Fitz-Nagumo equation, which has exactly sort of that structure. Yeah, and we have also applied this to quantum mechanics, to a dispersive problem that looks completely different, which is first order, where there was already a previous ad hoc result on the existence of slow manifolds by Gauvin Menon and George Haller. And our theory sort of incorporates this very special construction in that paper as a sort of general, part of this general theory. So this becomes a special case effectively. Yeah? So we can apply this to all sorts of evolution PDEs, which have this sort of timescale separation. And there we can identify nice Banach manifolds like in the Fenechel case. very good. So as we have seen, the problem is unfortunately not solved yet. So the problem becomes, let me do it maybe like 5 to 8 minutes before I end. The problem is not solved yet. So this is a bit more for the experts, because we have, of course, also in infinite dimensions, problems where we don't have normal hyperbolicity, where Fenechel theory even fails in finite dimensions. So if you have in finite dimensions this problem, you see that at the origin, there's actually a crossing of two parts of the critical manifold. And you see if you linearize in U, you get 2U for this ODE. And if you put in 0, 0, you see that indeed 0, 0 is on the critical manifold, and it's obviously not normally hyperbolic. It's even worse, it's not even manifold. It's actually two lines that are crossing, and there's no clear scale separation between the fast and the slow dynamics at this origin. Yeah? And classically, there's a proof that says if you perturb this system by some parameter mu epsilon, then for this transcritical type singularity, you can have two cases. You can either get attracted to this piece, flow up, and you have an exchange of stability and go to the left. Or for another value of mu, you get attracted, you flow up, and you make a jump in the fast direction. So this is a classical result for ODE theory in the plane. So how does this result generalize if I now make this a PDE? Let's put in all the PDE terms. Let's keep it simple. Do a reaction diffusion equation, bounded domain, Neumann boundary conditions, and ask what happens. So the question is how to retain this geometric interpretation. What objects to blow up? So in finite dimensions, I have a point, like what do I blow up in infinite dimensions? I cannot just take this point quite easily and make it into a sphere. That doesn't work in infinite dimensions. How to treat the spatial domain. Yeah, so what to do with the A. Yeah? And what happens in sort of certain types of this blown up manifold dynamically. Yeah, so if you blow it up and you look in charts on this manifold, what can you see on this manifold when you flow towards this point? All right, so what we have actually done is we try to do this sort of concrete example. The question you might ask is, why start with this transcritical bifurcation point? Let me explain this briefly in a minute. Well, first of all, it's a sort of manifestation of a very classical theory in PDEs from Crandall-Rabinowitz. It's a branch point for a standard sort of nonlinear elliptic equation. So if I would just take the first equation, I discard all the epsilons, and then this is a nonlinear elliptic PDE. And indeed, if I vary V as a parameter, I see that there's a bifurcation point, and this can be treated with classical Lyapunov-Schmidt, and it's a Crandall-Rabinowitz branch point where there's a new branch of solutions coming out. Near constant solutions, so if you take this TC evolution problem, the solutions that are near constant somehow should behave like the ODE. There will be other solutions, but at least you could try to hope that if you're sufficiently close to constants, you might hope that this transition near this transcritical singularity should behave a little bit like an ODE problem. Yeah? Fine. And there's non-trivial fast dynamics, so you have actually this mu parameter that is interesting. And the problem itself is very well posed, at least locally. Yeah? So locally near this point 0, 0, you have a nice parabolic regularity, a well-posed problem. If you cut it off on a certain ball, it's even globally existent. So it's a very nice PDE problem to start. And what you do, well, what we do is we first augment the dynamics also with the spatial domain. So we not only augment epsilon, but we also augment A. So A prime is equal to 0. So we make the domain dynamic. Yeah, we have now developed a second approach where you might not need that, but here we did it. So then we take a geometric space. Our new phase space will be L2. So it will be an infinite dimensional phase space. We assume that the initial data is sufficiently close to the constants. And what we do is we discretize. So numerical approach, we discretize in space. So we do a spectral Galerkin approximation in space. And then we do a blow-up transformation of every sort of finite dimensional Galerkin system. So this actually gives us a sequence of problems. And this sequence of problems are finite dimensional ODEs. And for every sort of member of this family of finite dimensional problems, we apply a blow-up technique. And then we analyze this, and then we show that basically for any arbitrary fixed k, 0, where we cut off the Galerkin approximation, we can fully control the geometry of the trajectories. So the proof is that effectively in infinite dimensions, the same picture as in finite dimensions holds true for any k0. So if you take all the other stuff with the Laplacian and so on, you can actually prove via this geometric blow-up technique that you do desingularize this transcritical singularity, and that you have two cases, the exchange of stability case and the jump case. So roughly speaking, this picture here is still true in infinite dimensions, sort of modulo, sort of slight variations, if you're starting close to the homogeneous solution. Well, that's sort of expected, yeah, intuitively. But the geometry is nice because we can now finally have lifted the blow-up method to infinite dimensions by doing it effectively on every finite Galerkin level. We can do invariant manifold theory and calculating the maps, how you flow, to arbitrary accuracy depending upon K0. And we actually see that the domain, this A, somehow has to deform while you're moving through this region of the singularity. And you even find some hidden PDEs in certain parts of this geometric blow-up construction where the domain is actually deformational. So there are sort of sub-PDE problems that by themselves are very interesting. So roughly speaking, you should say, well, you're moving with this PDE towards this singular point, you shrink the domain, yeah, and after you have shrunk it, you sort of analyzed it, and then you sort of re-expand the domain. That gives you effectively why there are free boundary problems around. Yeah? But it's very curious that now we have lifted this sort of blow-up method that took us a long time. At least a first step of this lifting has been done. We are working on many variations of this blow-up method. So let me briefly say this. I won't go through the details because I'm running out of time. We can show that the manifolds we get via discrete Galerkin approximation are actually close to the manifolds that we get via the abstract Lyapunov-Perron approach in the normally hyperbolic regime. So before manifolds, this is roughly saying in this bits here and this bits over here, where you're normally hyperbolic, everything's consistent. Yeah, so we can prove that. All right, so this is the last slide. Hopefully I'm roughly in time with 50 minutes, if that's perfect. So let me do 2 minutes for wrap up, then I have the 50 minutes nailed. So the outlook is we're doing other singularities. We're not only doing the transcritical, the fold is almost done and other singularities are also currently in progress. We are developing variants of the blow-up, not only the discretized blow-up, there are other variants of this blow-up technique that we develop because it's strictly necessary to do that. Actually, even if you're in the machine learning business, for example, you will see that most of these machine learning algorithms boil down to the fact that somehow you have regions where you're normally hyperbolic and other regions where you're not. And you somehow have to actually figure out how to glue this all together. And why this works is basically intrinsically a problem of how in infinite or very large dimensions gluing certain types of manifolds and trajectories together the right way. So the third question is, how do you do non-standard form systems? So systems that are not in the form where the epsilon is just in front of the last sort of variable. Yeah, the epsilon could be somewhere in the system, right? And it still could be fast, slow. Yeah, because it's a PDE, the epsilon could be, just say in front of the diffusion, for example. So how do you deal with these guys? We are actually dealing them right now. So there's a new postdoc coming in who will start to work on this relatively soon. And there are many, many further open questions in the area. So this area of multi-scale PDEs and how to attack them with dynamical systems and geometric methods, that's basically, exploding right now because it's needed everywhere. And lots of people sort of realized, okay, it's worth to work on this. So it's very active. So if you have interest in it, please come talk to me. I'm happy to talk about sort of all these problems in this area because it's sort of close to my heart. And if you want more information, all these papers and stuff is freely available on my website that tries to be easy to remember by its name. And then I thank you very much for your attention and hopefully I am halfway on time. Thank you.